This is our first problem on the natural response of first order RL circuits, and we are required to find the initial value of I, following the fact that the switch has been closed for a long time and is opened at time t. So in order to find the initial value of I, we have to consider the position of the circuit before time t equals 0, and the circuit will look something like this. And first off, in order to calculate the value of I, we want to know the total current in the circuit, and we do that by saying I, let's the total current be capital I, 100 over the equivalent resistance in the circuit, and that will be, since these two are in parallel with one another, the equivalence will be 20 times 5 over 20 plus 5, and then the two of them together are in series with a 1 ohm resistor. So all of this will be 4, and that will be 100 over 5. That will give us 20 amperes. And because this is the direction of flow of the current, we can use our current divider formula to calculate the value of minus I, and that would be 20 over 20 plus 5, 25 multiplied by 20, and that would give us 16 amperes. That means that I is equals to minus 16 amperes. So the initial current across the 10 millihenry inductor is minus 16 amperes. Next, we are required to find the initial energy stored in the inductor, and energy in an inductor is half Li squared, and that would be 1 over 2 times 10 raised to the power minus 3 times 16 squared, and that should give us 1.28 joules. The next question requires us to find the time constant for the circuit for t greater than 0. At t greater than 0, we are dealing with a circuit that looks like this. We have a 10 millihenry inductor and a 4 ohm inductor, and recall that the time constant tau in an RL circuit is L over R. So that would be 10 millihenry over 4, which would be equals to 2.5 milliseconds. For the next question, we are required to find the numerical expression for I of t for t greater than 0. And I of t, if you recall from our explanation on natural response of an RL circuit, is I naught e raised to power minus t over tau. So in this case, it will be 16 e raised to power minus that's 1 over 2500. That will be 1 over 2.5. That will be 400, and 2.5 milliseconds, that will be 400 over multiplied by t, that will be 16 e raised to power minus 400 t amperes. So that is the value of I of t at any point in time. Next, we are required to calculate the percentage of energy dissipated in the 4 ohm resistor after 5 milliseconds. The way to do this is to calculate the power, an expression for the power. After I calculate an expression for the power, you integrate with respect to time. Now, power P is equals to I squared R, and this would be 16 e raised to power minus 400 t squared multiplied by R, and this would be in this case our R is 4 ohms multiplied by 4. This will be 256 e raised to power minus 800 t multiplied by 4 to give us 1024 e raised to power minus 800 t. So to calculate the energy that has been dissipated after 5 milliseconds would be integral of from 0 to 5 times 10 raised to power minus 3, 1024 e raised to power minus 800 t dt, and you can do this with the help of a calculator, and that would be integral 1024 e raised to power minus 800 shift alpha x 0 5 times 10 raised to power minus 3. That will give us, we're just going to have to wait a while for the answer. Ah, 1.256 joules. Let's round that up to 1.26 joules, and the percent, we're required to calculate the percentage, so that will be 1.26 over 1.28 multiplied by 100, and that will be equals to we divide this by 1.28, then multiply the answer by 100, and that will be equals to 98.17%. So in essence, we're saying that after 5 milliseconds, the inductor would have dissipated 98.17% of the energy that was stored in it initially.